Okay, so it seems like there's quite a lot of people on the call now. We're going to go ahead and get started. So welcome to this, the second in the new series of webinars from the Cloud Native Computing Foundation. Today we'll be talking about cloud native networking, and we're very fortunate to have two very knowledgeable speakers with us. Christopher Lilienstolper, who is the CTO and co-founder of Tigera.io, and they are the people behind Project Calico, which some of you will probably know. Brian Borum is also with us, and he's a director of engineering at Weaveworks, who are currently working on Weave Cloud, which allows teams to connect, monitor, and deploy containers and microservices. Now, cloud native networking is a space that appeals to both network engineers and the growing number of developers who find that networking is becoming a part of their daily work. We've deliberately avoided heavy networking jargon to make sure that everyone can follow. But having said that, there are likely to be questions, so please drop them into the Q&A or into the chat window during the presentation. And when the presentation is over, we'll go through the questions then. Christopher and Brian, are you ready to rock?
Yes.
Yeah.
Good, well then take it away.
Okay, whoop. Mark, or sorry, Brian.
Yeah. I think we want the next slide, don't we?
Yeah, we are. So, sorry about that. A little bit of pointer problems on my side. So, what we're talking about here is networking for containers and microservices, and I thought it might make sense to put a bit in context within the CNCF reference architecture. So, CNCF reference architecture, for those of you who aren't familiar with it, is basically divided the landscape up into five layers of infrastructure and components. The actual physical infrastructure, bare metal, networking hardware, storage hardware, etc. The provisioning of that infrastructure and getting it ready to run cloud native cloud native tasks and functions on it. Then you actually have that runtime layer, and that's where things like resource management, container management, managing the compute resources, scheduling, as well as things such as networking and storage. And the networking is both of the networking and storage is basically based on plug-in models where different providers of that technology can plug into the infrastructure. And then above that is obviously the orchestration and management platforms, and then the actual application delivery and development. So that's where we're talking about today, is in that runtime layer of the CNCF reference architecture. So Brian, why don't you talk to us a little bit about where we started with container networking back in the earlier days of container infrastructure?
Yeah, way back, like 3 years ago.
3 years ago.
Yeah. So we got a picture on the slide here, and this is kind of trying to indicate one of the key problems that people faced when you run up a Docker container. It gets a network interface. It got one 3 years ago, but those were connected to a bridge which only worked on one machine, on the machine that those containers were on. And you could bring that port out to the machine's network interface. So that's the interface we show in the middle of the picture. But then you had this problem. What if two containers wanted to listen on the same port number? So port number, we mean the number that indicates what kind of a service you're going to offer. So a web endpoint is port number 80, a DNS endpoint is port number 53. So there's all these numbers they're very well known. Clients know which port to connect to, but you can only listen to one port from one place on a particular network interface. So this is the problem that this slide is trying to illustrate, that if you happen to have two containers that both wanted to listen on port 80, then what you ended up doing was remapping those port numbers. So in this example, one of them comes out on port 32768, one of them comes out on port 32769. Those are not well-known numbers. Those are numbers the client is going to have to find out. So now you have this additional bookkeeping. You have to keep track of those numbers. You have to be able to look them up. Maybe there's maybe some extra service required to do that service discovery. So this is kind of where we were 3 years ago. People were doing this. They were port mapping, and it was kind of ugly. Next slide. Yeah. So the idea, not that brilliant, I guess. Give each container its own IP address on a container network, on a network where all the containers on all the machines are going to be able to talk to each other. Yeah, so this was, yeah, in this picture that just shows the client just connects direct to port 80 because there's a container network now that connects up those two endpoints, and every container has its own IP address. You can listen on the same port, any port you want to, on that container network, and they're all connected up. So over to you, Christopher, for the next slide.
Sure. Yeah, so there's a number of advantages to this approach. You know, as Brian said, the port clash disappears. Now each container can expose port 80 service because of that. Now discovery of that workload, discovery of that service being provided by that container is now a DNS lookup. You know, we know, for example, that this kind of architecture works at scale. This is basically the infrastructure that the public internet is built on. You know, your services on the public internet all have their own IP addresses, and then there's a whole bunch of mechanisms that allow you to discover those services and connect to them. They've already been developed to work at very large scale. The interesting thing is that Kubernetes, as a container platform, took this approach from the outset. They were the first ones really to say, from the get-go, let's just give every container, every pod in Kubernetes case, its own IP address. Now, a lot of the other container platforms have done that as well, but you know, it gives you some advantages. You know, DNS we know works at scale. You can, you know, DNS is now natively supported in Kubernetes for service discovery like it is in some other platforms. But this just basically gives you a nice scalable way that with lots of tools already existing to connect to these services. However, in order to do this, you now need to do a little bit more networking in the host than a simple bridge. So how are we going to do that? What are we going to do within the host to make sure that each pod can get its own IP address?
Yeah, how indeed. Well, it turns out there's a huge array of facilities in the Linux kernel dedicated to networking. People have been building routers and firewalls and all kinds of network devices for decades on Linux, and it's immensely powerful. A lot of facilities. So basically, from the point of view of someone wanting to invent a container network, it's really putting together facilities that are already there in the Linux kernel. That's great news. It's very high quality features and very available to anyone who's running on Linux. The bad news is really there's a lot of choice. And you have to pick one. You know, if you've ever surveyed the market for container networking, you will find quite an array of offerings out there, and that can be quite bewildering. And we're going to get into some things to look out for as you look at which one you want to pick later on. But yeah, basically, we just put together some of the interesting features that are there in Linux, and we create a container network out of software.
So, you know, Brian, what is that? You know, what does a networking solution look like? What are the components that we're putting together?
Yeah, we split it just like the picture says into two things, which we call the control plane, the data plane. The control plane is all about coordinating things like the addresses, the routing of packets and things like that. And then data plane is actually transporting the data that's in the packets that you want to send from one container to another. Let's get a bit deeper into that on the next slide.
Yep. There we go. Sorry.
That's okay. Yeah. So as I was saying, the control plane has the coordination. So things like the IP addresses. There's probably a pool of IP addresses that you're using for your container network, and those are different from the IP addresses on your regular network. So the containers can happily come and go and talk amongst each other. The routing information, how am I going to get to a particular container, and also maybe policy, which is another thing we're going to get into in detail later. But a lot of people are pretty keen on having control over who can talk to whom on the container network. So that's the control plane. The data plane on the right-hand side of the picture. Sending the packets. Everything on your network is broken down into packets. So each one of those has a source and destination address. All we have to do is get them to where they're supposed to be. And in the middle of that, we might be checking whether they are allowed to be sent there by the policy. So that's the data plane.
So now maybe a little bit more into some of the specifics of how control planes are built and the kind of technologies that you commonly see within container networking platforms. You might be using a distributed key value store. So this is like what's used by Flannel or Calico. etcd is very common. There are other solutions out there as well. But etcd seems to be the most common distributed key value store that's used. You may use routing protocols. Again, Calico uses BGP. There are other routing protocols out there, and that is used to potentially distribute, as Brian said, reachability information. It's also good for talking to classical networking hardware that might also exist or does, in at least in private cloud, very often exist within the infrastructure. So this allows the cloud, potentially the cloud platform, to talk to that infrastructure if it needs to. There's also the use of gossip protocols, which are completely serverless, peer-to-peer state sharing infrastructures. It's used by, it's WeaveMesh, for example, implements a gossip protocol. It's used by WeaveNet. And then there is another model, and it's more common in the SDN solutions that came out originally supporting virtual machines, original generation of SDN environments. And that's a centralized controller where you have a process that basically, instead of in a distributed state, makes global decisions about what the network's behavior is supposed to be, and then signals that behavior down to all the various endpoints in the network. So those are some of the control plane options that you see in these environments. And there is no one thing that's best for every use case. So it's part of, we'll talk in a little bit about some of the things you need to think about as you're selecting your network solution for your container environment. All of these things have trade-offs. So, now let's talk a little bit about data planes. So now we know, where we're supposed to go. We've maybe learned what our policy is through that control plane. How are we going to implement that? So there's two really aspects to transport. One is the actual forwarding engine. What's going to be making the decision about sending the packet, figuring out where actually putting the packet onto the right path to get to the destination, and also applying that policy filter if you're using policy to decide, should A be able to talk to B? So it makes a decision on how to get traffic from A to B, and then should that connection even be allowed? And that normally takes place either using classical Linux kernel networking functions, either at Ethernet or IP layer, or potentially using a user space agent that sits outside of the kernel and makes that forwarding decision without involving the kernel in any regards. So OVS can be used here. That also has kernel capabilities as well, or user space routers. Then there's a transport mechanism, and there's some differences here as well. You may decide that you want to run just on the underlying network, and those containers or pods are actually part of the underlying infrastructure. They're actual nodes on the underlying infrastructure. That's we might call native networking. That might have some advantages if you're already in an encapsulated network, or you've got a network that will allow you to do that. If you can't put those nodes, those workloads directly on the underlying infrastructure, you might decide to use an overlay. And very often you'll hear people talk about VXLAN or IP and IP encapsulation. But basically what all that is doing is taking the packet that came out of the workload and encapsulating it in another packet, as you can see in the diagram here, to get it to the closer to the final destination, where it will then get unwrapped and presented to the other destination as the packet that was originally sent. And again, there are trade-offs to both of these, and in some cases you might want to pick one or the other, but that's when we talk about transport. That's really what we're usually talking about. Is it an overlay or a non-overlay infrastructure? Brian, you want to talk a little bit about plugins? Now that we've talked about how we're forwarding the traffic, how do those things talk to the orchestrators and find out what's going on?
Yeah, so we've given a kind of an idea of where some of this choice comes from, these decisions about whether it's a kernel implementation, whether it's overlay, non-overlay. Different people will prefer different choices, and so it's pretty important to a lot of people not to get locked into their to one choice. So the various providers recognized that and came up with a plugin model. So you pick your kind of outer infrastructure, and then you pick your network, and there's a plugin to go between them. A little bit of a annoying point right now in the world. There are two main plugin models. So let's talk about those. On the left, Docker's model, which for most of its life people used to talk about as libnetwork, and they more recently they've branded it as CNM, the container network model. And on the right, the CNI, the container network interface. So these two different models do have a different philosophy at base. The libnetwork is very tied into exactly what Docker does. And there are advantages to that, that it fits that model really, really well. There are disadvantages. It may not fit exactly what your particular network implementation needs to do. The CNI, on the other hand, is a very, very loose coupling. It is almost just a single instruction from the infrastructure to the network to say, add this container to the network. And how it goes about it, it can do anything it needs to do. So as you can see from the picture, a lot more people, notably Kubernetes and Mesos, have gotten on board with the CNI, with that model, but not Docker. And that's a subject of ongoing discussion. But that's where we are today with plugins. So you probably already picked your preferred orchestrator or platform. So from there, that tells you what kind of plugin you need, and from there, go look at the provider of network technology and make sure they have the right kind of plugin.
So let's talk about selecting plugins.
Yeah, wall of text. So we wanted to give a little checklist, and I don't think I'm gonna just read through every single one of these points, but here are some points to think about as you, if you're going to be out there selecting a container network. You know, which features do you need? Think about the flexibility that it offers. Take a look at how easy it is to set up. Resilience, I think, is an important point, because computers fail. So all this stuff implemented in software, what impact is a failure going to have on your overall system? First of all, the software crashes. Secondly, if the machine it's running on crashes. And lastly, if the network link that it is running on top of, it gets lost, what effect does that have? It's what we talk about, a network partition, and whether everything stops in that event or whether we can carry on one side of the partition. Those are interesting questions to look at with your choice of network. Do you want to take the right-hand side, Christopher?
Sure. And again, so, sort of dovetailing into resilience is monitoring and troubleshooting. Are you going to be able to troubleshoot and monitor and understand what's going on in the infrastructure with the skill sets you have? So if you pick a platform, for example, that leverages basic Linux networking concepts, and you've got a whole lot of tools, and a lot of folks who run Linux can sort of troubleshoot those kind of infrastructures reasonably well. If you pick a more complex infrastructure that, say, uses MPLS encapsulation or something along those lines, then you're going to need to have different sets of skill sets and more higher end networking skill sets in order to monitor and troubleshoot. So the test I usually use there is the 3 o'clock in the morning test. If it breaks, will the person who's on call at 3 o'clock in the morning be able to figure it out, or will they have to wake someone else up to figure it out, or call in a team? And something to think about as well, because things never break at 10 a.m. They always break at 3 a.m. Is what kind of security do you need? And I think some of the things you need to think about here a bit, we'll talk a little bit about this more in policy, is that this is a much more dynamic environment. So if you think that you're going to be doing security in a very static way and just putting some basic perimeters around there, it may not work in a cloud native environment. So assess what your security needs are, and will this kind of, the platforms you're looking at give you the kind of security requirements that you meet your security requirements. And scale and performance. There's a lot of folks don't need the highest performant network around, but you do need to think about scale. The whole idea about container, cloud native container environments, as they scale up, they scale down, they're very dynamic. So what's that going to do to your performance? What's that, as you add nodes, as nodes are very ephemeral and come and go, what kind of performance impacts is that going to have? Are you going to be able to meet your SLAs? And you need to take a rational look at that. Is not, what are your actual workloads? What are your actual SLAs that you need to provide for, and understand how those are going to be impacted as the network changes over time. So don't gold plate something that doesn't need to be gold plated, but also understand how it's going to behave as it scales up or out.
Yeah, and I get to talk to, in my job, I get to talk to a lot of people about benchmarking networks and container networks, and a couple of points there. I think do a realistic benchmark. So many people pick on some micro benchmark that does something extremely unrealistic, like one thing that sends packets as fast as it can. That isn't going to tell you how your real system is going to behave under load. So so use a realistic benchmark if you're going to measure the thing, and also beware of cloud when benchmarking. If you think about it, you're renting space on someone else's computer. The benchmarks you get one week might be different the next week because your VMs have landed in a different rack, or maybe a different segment of the network. Maybe the segment you were using was very congested last week and it's less congested this week. These are real difficulties with trying to get accurate information unless you put a huge amount of effort into trying to control for all the variability. So bottom line, do some testing with a realistic workload, and I think you'll find almost any of the options out there are perfectly satisfactory, because unless you're like a high frequency trader, which used to be my job, yeah, unless you're doing electronic trading, that kind of thing, you're really not that sensitive to the low level behavior of the network.
And I think, Brian and I both have operational experience as well. And I think I'll Brian can say I'm wrong here, but, if you are going to go down the testing, the testing path, one thing to keep in mind, this is one thing we always did when we were building production infrastructure, is I just don't, if I'm going to test, there's actually two values to testing, two benefits to testing and getting some of that information back. One is it fit for purpose? The other is understanding how it misbehaves when it goes beyond its design goals or whatever else. How does it degrade? We used to test things not necessarily to validate things, but test them until they broke, quote unquote. So you actually understand as an operator that, okay, when I lose 50% of my infrastructure, or it scales up on a Mother's Day event to 5 times what I thought, is it going to degrade gracefully? Is it going to go boom in the most amusing manner? But you do need to sort of understand, how is this thing going to behave in under stress situations? So that's something to look at as well. If you're going to do this, you're going to spend, as Brian said, the resources to test and evaluate it beyond the point where you think everything will never go beyond. Take it out and see how it behaves when you start putting it under real stress.
Okay. So
we hinted a little bit about security, and as we say here, one does not simply secure the perimeter. Security used to be very easy in the classical enterprise days, where you had a single application, it had firewalls protecting that application, and that application really only talked to the users. As we go to this more microservices environment, we started doing this in VMs, but now really in the microservices environment, that application very likely is doing more effort servicing other applications than actual end users. It's very much more of a mesh in your data center. And because one of the advantages of cloud native is that you can place the workload anywhere. You don't have to start thinking about physical adjacencies, etc. You treat the underlying infrastructure as one big fungible fabric, and you allow the scheduler to be as efficient as possible in placing workloads wherever they go, and workloads can independently scale, etc. If that's the direction we're going, one of the problems it has is that the endpoints that you want to protect are now also very dynamic. They change in number, they change in location, etc. The orchestrator knows where all those things are. They know how things are scaling, etc., be it Kubernetes or Mesos or Docker, etc. So there's knowledge in the infrastructure as to where these things are, which is potentially useful. However, people who have wanted to try and use their existing security infrastructure to protect these platforms have realized that the only way to really do that is to just put a perimeter around that cloud infrastructure, because the legacy security kit they're using can't talk to these orchestrators. So what you end up with is this firewall, and you've got, and we talk about attackers here because it's sexy, but this could also just be poorly written code that goes insane inside the data center and tries to talk to everything all at the same time. Nonetheless, you've got a firewall, it's just protecting that outside link. When you have a malicious actor that gets past that firewall, either by spear phishing, social engineering, or incorporation of bad code. Somebody did a git pull from a repo that they maybe shouldn't have by accident. You now have a actor within your infrastructure behind that perimeter who now has basically access to everything. And this is the way a number of the very large hacks that have happened over the last number of years has happened. Somebody gets into the infrastructure, there's now no controls on the inter-application or even intra-application traffic, and they can go all over the infrastructure, map out where the interesting bits are, and eventually get the data back out.
And that's a mean-looking shark there.
Yes, I know, it's a wonderful, mean-looking shark. I think the thing you have to be aware of is that people will get into your infrastructure. And as your infrastructure gets very dynamic and gets very large, it's not going to be a matter of if, it's going to be a matter of when or how many things are going to be bad actors in your infrastructure, either intentional or unintentional. So you not only have to protect workloads from other things, you actually almost have to protect workloads from themselves or from other workloads. So what you could do is you could use the information that's in that orchestrator to actually state what things need to be able to talk to what things and where they are in the infrastructure, and then start applying policy such that only connections that the developers and the operations team have decided make sense are allowed. So, an LDAP server maybe only really needs to allow traffic from things that are LDAP clients on the LDAP port, and it doesn't need to receive traffic on all different kinds of other ports. So maybe you can express that in such a way that wherever an LDAP server, an LDAP client comes up in the network, a policy is applied that allows that connection and blocks others. So if you do that, then you end up with a point where even if a bad actor gets in, his blast radius or a piece of bad code that overruns the infrastructure is now constrained in the damage it can do. And one way of doing that is, let's think about a very simple case. In a 3-tier architecture, blue, yellow, green, those workloads are showing up anywhere in the infrastructure. And depending on scaling, they could be changing on a second-by-second basis. How do I provide, for example, the classical 3-tier architecture protections in this cloud environment? If I'm running this, for example, in Kubernetes, I can use Kubernetes policy. We won't go into the details here, but you can basically attach a policy to each of those things. The blue is the front-end policy, and it basically allows traffic from the public internet. The green boxes are the middle-tier policy, and they'll only accept traffic coming in from the front end, and they're only so they can't be connected to by anything else. And the database tiers, the yellow boxes, will only receive traffic on database ports from the middle tiers. So, this is very simple policy. You attach them to the pod specs in Kubernetes and the policy API in the Kubernetes infrastructure. And then whenever a blue, green, or yellow workload shows up, it gets this policy automatically attached to it. And what you end up with is something that looks like the security policies we used to do in classical siloed infrastructure, but now in a cloud native manner. In this case, the only things that can talk to the Redis database are the middle tiers, for example. So this is the benefits of policy and linking policy into that orchestration system in real time. And this is, I think, a differentiator in some of the cloud networking platforms. And this is where you can get some real additional value in cloud networking beyond just the simple scale out. Is now you can scale your policies as well as your actual just network connectivity. And
so let me try and sum it all up. Thanks very much for that run through of policy, Christopher. So when we talk about cloud native computing, we're thinking of a much more dynamic infrastructure, much more flexible, scale up, scale down, things coming and going, spin up new containers much faster than you span up virtual machines in those ancient days of a couple of years ago. And so in that world, we may need some new networking technology. We're definitely going to need some networking technology, but the new technology of container networks completely implemented in software, that software is heavily reusing modules which are in the Linux kernel. And that's a great thing. But it's all done in software that gives you a whole new flexibility and a whole new power. At base, it's a very simple model. Each container has its own IP address, and they're all on one network. They can talk to each other. That's the way everyone does it. That's the simplest way to move forward. And you just do a DNS lookup when you want to find the thing you're looking for. Having said everyone's on the one network, that brings those concerns about how do you stop being able to connect to the things you're not supposed to connect to, and that's the whole policy story that Christopher just gave us. And then we went into some depth in many of the choices that are out there, which leads to a lot of variety in the market, which is a great benefit for people who want to use this stuff, and it's also a curse because you have a lot of choice. So we went through a big long checklist, which is in the middle of the deck, on how you can try and make those choices for your own situation. So thank you very much for listening. I guess I'll hand back to Mark now to consider the questions that have been asked.
Hello, and thank you very much for what was a very interesting presentation there. We got a couple of questions in. I'll just read the first one out and you can decide who answers. Should we do it like that?
Sure.
Okay, so the question is, you say that giving each container its own IP works at large scale. Can you quantify that?
So why don't I take a first shot and then
Sure.
Brian. So I think the issue that the question might be referring to is IP address exhaustion. I mean, we know IP networking works at very large scale. We have a very large proof case out there. We're using it all right now as we speak. There may be issues in certain organizations with IP address exhaustion. There's a fairly large space in 1918 space and some other spaces that can be used, IP address ranges that can be used. But if you're talking about very, very large organizations with very large
well, maybe it's important to stress that when we go to the container network, we generally start in a private space. Yeah, I guess it's difficult without knowing exactly where the questioner was coming from, but they're within the IPv4 space where there's only a few billion possible addresses. There are these large segments carved out as private spaces, and we tend to use one of those when we're setting up our container networks. You can certainly get into the millions, tens of millions of addresses very, very easily. And then if you did run out, IPv6 is the place to go. As of right now, much of the container networking space does not do IPv6. So that's certainly a reality. Kubernetes, for instance, doesn't handle pods with IPv6 addresses, but it is something that's being worked on, and I expect if anyone actually had a real problem there, then people would fix that fast.
I mean, there is some activity actually right now and starting to discuss more seriously IPv6 in Kubernetes. And the thing to keep in mind is, since we've leveraged, and a lot of folks have leveraged sort of the existing infrastructure and tooling for networking based on Linux and protocols, etc. All of those things support v6. So it's not like there is a technical hurdle in actually implementing v6 in a lot of these platforms. It's really just waiting for the orchestration platforms, etc., to catch up. I'll echo what Brian said. What we see is most folks deploy their containers using private addresses, or a very large pool of private addresses and a smaller pool of public addresses that are used for front-end load balancers or other things that would be connected to the public infrastructure. So, we've had one or two folks who have, honestly said, yeah, eventually we're going to exhaust that very large private space within v4, but I haven't seen anyone today come a cropper against, not being able to deploy because they don't have enough private v4 address space.
Yeah, so that's the quantity angle on that question. The questioner may have been thinking from a speed point of view as well, because there's going to be some coordination amongst all the hosts of who gets which address. And I think most of the implementations work by kind of grabbing a bunch of addresses at once. So there's some kind of interlocked exchange whereby a host will get hold of a few hundred addresses and then use those, and then when it runs out of those, it'll grab a few more hundred from the millions that are available in the big pool. So that's a very brief outline of how you amortize the costs of coordinating that problem. So yeah, I don't think there's a real fundamental issue there.
Right, and we know how to manage very large IP networks. We've been doing it for a long time. There's all sorts of technologies, like Brian said, pre-allocation. There's potentially route summarization, etc. There's the nice thing about taking this IP endpoint-based approach is we get to leverage all the tools that have been developed over a very long time to manage these very large IP networks. And that's sort of standing on the shoulders of giants. This work has already been, I'd love to say we've created all this ourselves, we're incredibly brilliant, but in reality, we're leveraging the tools that have, that have been developed by a lot of very smart people over a very long period of time.
Yeah.
Thanks for that. So there's quite a few questions coming in now. I'm going to jump into one that's come up twice. Will a recording be posted, and if so, where? Yes, a recording will be posted. I'm just putting the link to the CNCF YouTube channel now into the chat. You will see in there the recording of the first webinar we did with Jamie Dobson about cloud native strategy. This one will be posted there, I guess, within a couple of days. And someone also asked whether or not we would be giving the slides away. Yes, we will. And they asked, will it be available as PDF? I think what we're going to do is give you a link to the Google Slides, and you can download your own PDF if you want to. Next. Are there fundamental differences between a routing protocol like BGP and a gossip protocol, e.g. a mesh, for the control plane?
No.
Yeah, I tend to agree. And there is no central controller, or there are ways you can build relay nodes within BGP to reduce the number of things you have to peer to, but BGP as a protocol and gossip protocols are pretty much flood the information out along a graph and that you discover, and eventually everyone converges, everyone agrees on the data that's there.
Very good. Okay, up next. How do these technologies work with global deployments? Assume you need hybrid technology to link many private container networks across the globe or data centers by bridging or VPNs. Do you still get the same benefits?
Whoa.
Shots fired.
I think there's a larger question here. From a networking standpoint, again, because we're leveraging this sort of IP-centric approach, there's lots of tools out there and lots of mechanisms that exist to allow you to link, disparate, disconnected or disjunct infrastructures together and allow them to talk, be that VPNs, be that tunneling infrastructure, etc. We've got lots of folks who are doing hybrid public-private cloud, for example, or multi-public cloud. And that sort of pretty much works. I think there's a bigger question right now, which is the orchestrators and the control plane for the orchestrators and how they'll work over disjunct infrastructure. So Kubernetes is having a large discussion right now and developments around what's called federation. And that's really, so it's not just a networking thing. I think it's the entire cloud infrastructure has to be able to federate or link together semi-autonomous regions. And as the orchestrators provide that capability, the network will come along for the ride as well. Brian, you have a
Well, that links back to one of the key things to think about in that space is the failure model. As you look at a bigger and bigger set of infrastructure, it becomes more and more likely that some piece of it is going to fail. And so a setup where there are thousands of things all over the globe, and in order for any of them to work, they all have to contact one central database in one place, is not a good model. That's what leads us to talk about things like federation. Like, how do you split that decision process? How do you have regions of control, or alternatively, how do you go to a design with no central control and an overall peer-to-peer coordination? There are different ways to attack that problem, but the fundamental thing to think about is what's going to happen if I lose this transatlantic network link. What's going to happen if some fishing boat trawls up the link between this country and this country? If I'm operating globally, these are the things you got to worry about. And building a system that doesn't have the behavior that the whole thing will fail if one piece of it fails.
So I'm going to skip past the question to the last one. There's two, but I want to go to the second one because it seems related to the point we were just making. And you're getting thank you from you're getting thank yous for the answers.
Thank you, Andy.
I don't know if they're supposed to be anonymous or not. So the anonymous viewer asked, I would expect that any SDN continues to work in the presence of an underlying network partition. I'm very surprised to hear that some SDN solutions rely on CP systems like etc.d to make forward progress. Am I misunderstanding something, or do these SDNs break when there is a partition or interruption in the physical network?
So, it's an interesting question, and I think this also gets back to in the case of raft-based consensus algorithms, this gets back to the concept of federation as well to address this. But I'll take, for example, the platform I'm familiar with, Calico. If etcd ends up being partitioned, if you end up, for example, with a split across two data centers and one can't contact the other, the part that has lost quorum will still continue to function. It just won't get updates from the other side. So, i.e., it's going to be running on the data it last had, as far as policy and networking, etc. Since it can't talk to the other side anyway, that's probably a reasonable failure scenario right now. And then when the network partition's resolved, it comes back into quorum. The Kubernetes but this isn't just a networking problem. This is a problem for any orchestration system that's based on a raft consensus algorithm. And that's why we're looking at, that's why Kubernetes community, for example, is using, is working on federation such that you can have multiple Kubernetes clusters that can be disconnected and reconnected. And obviously once that's, once you've solved that problem for the orchestrator, you've solved that for the network as well. The network is taking input from the orchestrator. So this is a problem the community has as we go to multi-data center, if those data centers potentially are disconnectable. And as Brian said, things happen in the network. But this is not just a networking thing. This is entirely an orchestration level thing at this point for folks that are based on raft consensus algorithms. And it's understood and actively being worked on in the community right now.
Yeah, and I should just add that some platforms choose to have eventual consistency, and that Tends to be a lot more work to get that to work right, but it does have the benefit that both sides of a partition can continue making updates.
True, and I think federation gets you to some to a eventual consistency behavior between sections within that between nodes within that federation or clusters within that federation. Eventual consistency is a win, and it's just a matter of at what granularity you do it and the mechanism you pick.
Thank you. We've come down to our last question now. That is, the arbitrarily variable performance based on placement is an issue. What are your thoughts on improving this?
Buy your own cloud. Well, seriously, if you're renting space, I think if you look in detail into the different cloud providers, I guess I spent more time reading up on this about Amazon, but I'm sure they all have more or less the same ideas that you can specify a bit about the placement of your machines. You can create subnetworks and ask that two machines go on the same subnetwork. You can't really ask that two VMs end up in the same rack, and indeed that might not be a very good placement from a resilience point of view. But you can make some choices when you kind of rent your machines from the cloud provider. But fundamentally, that is the model. You're renting space on someone else's computer, and it's a kind of a quality of service thing, whether they have packed a bunch of other people onto the same computer that can make that very variable or not. And probably gets better if you rent bigger machines. Again, all the cloud providers tend to have different instance sizes. If you rent those kind of tiny ones that only cost $1 a month, or I don't know, that's not realistic, but you know what I mean. If you rent the cheapest machine, you're going to get the worst variability, because that's the way they make the economics work. And if you rent a much bigger model, then the providers are not packing them so tightly into the racks, and you're going to get a better experience that way.
Yeah,
right.
So I think.
Sorry, go ahead.
Yeah, I think that's not really just a networking question, right? Because the network doesn't really dictate where a workload gets placed, and this is an orchestrator scheduler question, and we do hear this from not just people in public but also in private cloud. They want to be able to land certain workloads in certain racks and make sure certain workloads don't end up in the same racks, etc. And that's something that as the community wants that kind of capability. That's capability that would eventually get added to the orchestrators, to the schedulers, and that's something then that the network providers could leverage or could even give feedback into at some point in time. But I think that's not just a network specific thing. That's the scheduler is the thing that decides where workloads go and what resources get attached to them, and that's really how rich is your scheduler, how extensible is your scheduler.
I should just say we got a comment on the chat that somebody's saying we can dictate placement in AWS. So go read whatever your cloud provider is. Other cloud providers are available. Whatever your provider is, go ask them. Go check out their docs and see what they offer in terms of requesting particular placement of your VMs.
All right, thank you very much. That was the last question. Final thing I want to say is that, well, actually not the final thing, the penultimate thing I would like to say is that we have another Cloud Native webinar coming up on February 23rd. It's going to be led by Alexis Richardson, who's the chairperson for the Technical Oversight Committee at the CNCF. And he's going to be giving a talk that he first gave at Software Circus in Amsterdam, which is what is Cloud Native and why does it exist? So that's going to be a nice high-level talk talking about the history of this movement and why we're all spending so much time pushing it. All that's left for me to do now is say a huge thank you to Brian Borum and Christopher Lilienstolper. Thank you very much, guys.
Thank you for inviting us.
And thank you to all the people. Yeah, and thank you to all the people who showed up. It was very busy today, and we hope it's going to be busier on future webinars. That's it for now. Goodbye and good night.
Bye-bye.
Bye, everyone.